So you can take this, you can factor in this, but how do we do this? Well, I mean, I guess what you could do. Here's the shortest way I know to do this. And just hope this works out, right? No, I made a big assumption here that I've got ones here, but there's a certain symmetry to this polynomial because notice that the fourth degree term works, right? What are the cubic terms? Well, the cubic term is a plus b over here, right? Do I agree with that? The cubic term over here is 0. The quadratic term is ab plus 2 over here, right? And it's 0 over here. And here's the first hint that this might be something that works. The linear term is also a plus b, and it's also 0, right? So here I have two equations and two unknowns, and it's pretty easy to see that solves quadratic, and that's where the radical 2 comes from, right? But I mean, if you really want to confuse your, algebra class that you're teaching, right? Just write this down and, watch people throw their books and get very angry, right? Because this looks like this comes out of nowhere, right? That's your first problem, is you've got to know how to do this, right? Well, okay, so we're smart, we know how to do this. Now, it's easy to test that these two polynomials themselves are irreducible, right? Because either they are, or they break down into linear factors, which means the quadratic formula should tell you the roots. But if you check this out, when you square this minus 4 times b, that stuff that goes under the radical of the quadratic formula is negative, right? So these can't be reduced. So this is now you gotta solve that, right? Which is awful, right? I would multiply both sides of this equation by x to the 4th plus 1, which is the product of these two things. And so x 4 plus 1 kills this, right? This thing gets sucked out of the x 4 plus 1, and I get ax plus b times x squared minus radical 2x plus 1. And here I get cx plus d times x squared plus radical 2x plus 1. Agreed? Now we gotta solve all this, right? Now, what I'm gonna do is I'm gonna pretend that this is a polynomial, because it is. It's just got a 0 cubed term and a 0 square term and a 0 linear term, and 1 is the constant term. Let me ask you this. On this side of the equation, the cubic term is 0. Everybody agree with that? What's the cubic term on this side of the equation? Okay. The quadratic term on this side, 0. Quadratic term on this side, worse. Right? Minus radical 2a plus b, radical 2c plus d. Okay, so far? Linear term on this side, 0. Linear term on this side, a plus radical 2b, and c plus radical 2d. And there should be a minus there for one of them.
Yeah.
It should be minus radical 2b, and I better not miss that. Look better now? Finally, linear term, or I'm sorry, the constant term, 1, and on this side, b plus, right? Okay, so far. Now what? Well, now it's linear algebra, so now we've got linear algebra on this. Right, anybody see what we can do?
Get rid of your A plus C in the third equation.
Okay, so what we have in the third equation, the A plus C is 0, right? So this Casper is gone, right? And so the last two equations are actually and lucky me, this one actually that I can get rid of that radical too, can I? All right, so this is B minus D 0. And so now I've got sort of half of it in a certain sense. I've got B equals D. And I'm willing to bet that that little trick that Grant came up with the A plus C being 0, that's probably really I only needed what this equation, and it got me this. What about this? Well, B plus D equals 1. So now we've got to do everything else. Let's just throw B plus D in here. And what do we have here? This equation will be something like radical 2A minus radical 2C equals 1. And then I've got right. So that's what I've got when I threw that in, right? And so if I threw B and D as a half in here, what happens here? Those two cancel out, don't they? So I get A plus C. So that means A and C are opposite sign, and so I get 2 radical 2A is equal to 1. And so I get A is 1 over 2 radical 2. B is, or not B, but C is minus 1 over 2 radical 2. Now I'm going to hold these in reserve now. Okay. Let's just remember those. Because actually, it's easier to integrate this with the letters than with the numbers, because who cares about the numbers until we need them. So this integral becomes the integral from minus infinity to infinity of ax plus b over x squared. Gosh, I guess I better remember. Partial fractions gives us this easier bit. But okay, now what?
And go for use.
Right. So what technique should we use?
Pretty sure the signs are wrong.
Are they? Did I have the AX plus B over this or the other one?
It should be, yeah. That should be plus.
It should be plus. You better catch me on that, because otherwise.
Because for our like system of.
I didn't remember. Unfortunately I erased it, but that's what it was originally.
Pretty sure.
Okay, that's good. So how do we do this? Well, you're gonna love this. We need to complete the square, right? And so this is actually minus infinity to infinity. This is AX plus B over X plus, that would be plus squared 1/4. 1/2. There we go. That looks right. Now we gotta do that. Right? All right, I propose we do the following. I think I can remember this interval now. Let me just do this anti-derivative. Over well, let's just figure this out because it'll make things be convenient. I think I'm making my point very well, by the way. This is A times U minus A plus B over U squared plus little b dx.
du,
What's that?
du.
Oh, du, yeah, thank you. U, so this is the integral of A U minus little a big A plus big B over what is that B U. Now I'm gonna do this in my head a little bit because this U over U squared plus B is a log, right? So it should be like 1/2 A natural log U squared plus B. Agree? And I'm going to use another fact that you can easily do by a substitution. By the way, I know what this is. Sort of. It's we use that. So this should be B minus A times, this should be 1 over radical B tangent inverse X over radical B. Right, because this piece right here is just this constant 1 over U squared plus B, and using this formula with replacing the A squared by B. I get that. I meant to write you. Thank you. I seem to be doing that all over the place. And that's important because in our step here, then this becomes X plus A squared plus B plus capital B minus A. 1 over radical B tangent inverse X plus A over radical B. So what's this thing? Let's see if we can adjust our formula to it. And actually, I'm going to write this off the chalkboard here where the camera can't see it. So what should this awful thing right here be? Let's apply this. The first one is a direct application with A being 1 over the square root of 2, right? So the antiderivative should be 1/2 A natural log of, let's see, that'd be X plus 1 over radical 2 squared, and my B is 1/2. This actually turns back to if you actually square that out and add this, it comes, no surprise, right? Because it comes back to the original. So there's that piece. And then I have plus b minus a, which is actually 1 over radical 2. A is, yeah, 1 over radical 2. Times 1 over radical b. Now, radical b is 1 over radical 2. Tangent inverse of x plus 1 over radical 2 over 1 over radical 2. And I'm just going to leave it that way. That should be 1 over that, so it should be radical 2, shouldn't it? Is that right?
Other way around. The one outside should be right.
The one outside should be radical 2. The one inside won't make any difference. The outside one will. Yeah, so b is 1/2, so 1 over that, yeah. Okay, and the other piece should be, now, we'll see, we've got 1/2 c, natural log. Okay, this time we replace this with minus 1 over radical 2, right? X minus 1 over radical 2 squared plus b, so I get x squared minus radical 2x plus 1. And now what do we have? In this case, it's what? D minus 1 over radical 2c. That makes sense?
Plus. Because A is negative.
Because it's negative now, thank you. So that should be a plus. And then radical 2 again, inverse tangent, x plus x minus 1 over radical 2, radical 2. And now we just need to evaluate this from constant to infinity. Now, the tangent, the inverse tangent's not going to give us any problems, right? In fact, this function is bounded and it's very well behaved. This is problematic, right? Because what happens here is the log is going to infinity both directions. What does that mean? So I do need to combine this a little bit more. What do we know about A and C? They're the same thing up to a sign, right? This is actually 1 over 2 radical 2, and this is 1 minus 1 over 2 radical 2. Right? I agree with that. And so, what do I get here? Well, do I?
I think you should get 0. Yeah, you're gonna end up dividing one by the other, and then we take the limit to infinity, it's like.
Okay, there we go. So we get 1 over 4 radical 2 of this minus this. Everybody agree with that? Which is natural log x squared plus radical 2x plus 1 over x squared minus radical 2x plus 1 plus the rest of this awful mess. We'll say, because I'm a lazy man, into. Right. Now let's see what happens as we go to infinity. What happens as we go to infinity? This goes inside the parentheses to 1. So we got log 1, so this is gone. What happens to the M1 piece as we go to infinity? The inverse tangents, well, so this should go to power 2 times whatever this mess is. So this should be like b radical 2 minus a. Right? That's power 2, and this radical 2 goes in there just like that. And how about the M2 piece? Power 2 again, And this goes to D plus, or I'm sorry, it goes to radical 2D plus C times pi over 2. Now we also cruise out to negative infinity. And again, we're lucky with the negative infinity because we get log 1 0. What happens to M1 as you go to negative infinity? Well, the only thing that changes is this is a minus power 2, right? So this is a minus power 2. Everything else is the same, which we're subtracting it. And same thing here. Everything's the same, we're subtracting. So essentially, we just double this. So at the end of the day, what do we get? Well, we get, doubling that, we get pi times b radical 2 minus a. So, see, that's going to be 1 over radical 2. So that's going to be minus a. So that's going to be, well, let me write this. This pi times b radical 2 minus a, or 2 radical 2. No, I double that. So that's right. B radical 2 minus a plus b radical 2 plus c. So b radical 2 plus d, b plus d is b equals d is half. So b plus d radical 2 is going to be radical 2. And then minus minus a plus c is minus 1 over radical 2, I guess. Right. And so this is 2 minus 1, so it's 5 over radical 2. I can't believe I did that correctly, but, and I wouldn't have if you guys had stopped me a few times. Okay, everybody, I think I've made my point too well. Everybody agree that this is a nasty, nasty problem, right? Awful. Okay. I did this with calculus doing real variables. Now, complex numbers, I'm going to give you a quick crash course. We're going to do this. We're going to do this problem again, but before you call the suicide hotline, it's not going to be as bad, I promise. How many of you have seen complex numbers before? Okay, so the idea is you have a real axis and an imaginary axis. And I like to think of things two ways. How many of you remember polar coordinates? So Z is a complex variable. It's sort of got a real part and an imaginary part. And sometimes we write this way. And it connects with trigonometry quite well, already out there. How many of you have seen this identity here? How many of y'all have seen it? This is probably one of the most famous places. If you've had a really good trig course, you've seen this actually. If you want to verify it for yourself, and you've seen Calc 2, take the Maclaurin series for e to the x and shove I theta in it and see what happens. It'll break up into a real part and an imaginary part that will be cosine and sine. It's really kind of cool. So we might consider ordinary functions that we play with, like in the complex plane. So for example, you might consider the function e to the z. You might break this up into pieces. So you can think of this as broken up into pieces. So if you look at C in the complex plane, what does this tell you about it? This tells you that as your x coordinate is very large, either positively, then the magnitude of this gets very, very large, right? It's very big, right? But it can also take on negative values, can it? Right? Because of this term right here, right? So that's kind of the neat thing about it. Also, as x gets very, very large negative, this thing gets very tiny. Maybe it's even more surprising to do something like this. What about sine z? Well, sine z, using this identity here, that's cosine z plus I sine z, that's minus cosine z, minus I sine z. So divided by 2i and you get this. If you work this baby out, this one gets very interesting because I won't take up a whole lot of time doing this, but basically what you get is so this will be kind of a fun exercise. So the trig functions in the complex plane are not bounded, right? And actually this points to sort of an intimate relationship between the trigonometric functions and the hyperbolic trigonometric functions. If you work this out, replacing z by x plus iy and control this all out, you get this. And so remember, the hyperbolic cosine gets very, very large, right? And so the sine is unbounded in the complex plane. And perhaps thinking about it from this point of view, how would you do the logarithm? And this actually comes up and it's rather important in things like finding roots. Well, if I take the log, so let me just do something that's very very naive. But if I take the log of REI theta, you would want this to have properties of log that you would want. Right? That's what you would want to happen. You'd want the log of a product to be the sum of the logarithms. This is, of course, the real thing. If you think of the complex numbers REI theta, and this is just I theta. And of course, naively, I would think this is just I theta. And it turns out that when you take the logarithm of something, it's many valued. You have to pick a value. So where theta, if you take your z, how do you do the logarithm of z? Complex numbers. You take the logarithm of the magnitude of it, right? And then you measure its angle and add I theta. Now notice this depends on how you're measuring angles, right? So for example, if this is pi over 4, say, if you're measuring from 0 to 2 pi, then it would be plus I pi over 4, right? But if you're going from 2 pi to 4 pi, it would be a different answer, right? This is because you don't have unique representation in this thing, so you've got multi. Usually what happens to make the single valued is you pick a range for your angle and kind of stick to it. But so for example, here's a question I asked many years ago. This sounds like a really weird question. What is the smallest value of I to the I power? Yes.
E to the minus pi over 2.
That sounds right. We'll see. Or maybe I should say with value, we'll see what it turns out. So let's try to wrap our heads around this. Now, where's I in the complex plane? It's 1 unit away and it's at the angle of pi over 2, plus any 2 pi k. So this is the log of the absolute value of I is 0, right? Because the length of that is 1. So this is e to the minus theta. Oh, I guess it's probably without bound in both directions, because notice that you can take theta to be so, for example, you could have e to the minus power of 2, that's about a for I over I, depending on how you, I to the I power, depending on how you take it. You can have e to the minus 3 power of 2. So let me take smallest out of this and just say something like analyze. And of course, with that, you can take negative values too, and so this gets very, very large as well, right? Which is really weird, right? I to the I always turns out to be a real number, right? No matter how you pick your angles. Okay, here's the crash course. What you need, complex analysis. Now, how many of you have ever seen line intervals or contour intervals? You've had Calc 3, you've seen this. You've actually seen this in Calc 1 and Calc 2 as well, you just don't know it. When you integrate a function, you're integrating along the real line. That's it, right? But you could have your input coming all over the place, right? And in the complex plane, you've got 2 dimensions. So you might integrate from here to here along this little curve, right? And it's set up the same way. You've got your little values of the function, your little changes and whatnot. And so here's the important thing. Oh, don't take that out. Let's warm up to this. Let me give you a first fact. Where this contour, so I'm integrating along the circle one time around counterclockwise. Anybody know what this is? It's 2 pi. And I could prove this for you using calculus. Right. If you give me some liberties. Every element Z on the unit circle is a form EI theta, right? And you let theta vary and you go all the way around from 0 to 2 pi. Agreed? Correct? So this becomes the integral of 1 over Z dz. And to go around the circle, my theta starts at 0 and goes to 3 pi. Right? Check out this blood bath. Now, if I replace that, so this is Z to the minus 1 power. If I replace that with any other power, I get Z to the what do I mean? If I integrate around the same circle, I always get 0. Do I know where?
It's analytic.
Well, right, but I don't want to use any big guns here. Right? This is, let's do the same thing. So this is the integral of E I n theta the nth power of that, times I e I theta d theta from 0 to 2 pi. So this is the interval from 0 to 2 pi of e, well, there's 9 there, i.e. n plus 1 theta. Theta. You wonder why that's 0? This might help. This is the interval from 0 to 2 pi of I times cosine and theta. I sine, well, I guess it should be n plus 1, should it? And if you have an integer multiple of theta, what happens when you integrate sine or cosine over a 2 pi interval? You get 0, right? So everything drops out. So not only is this 2 pi I, but this kills every other power. Every other power when you integrate around there, 0. So if you were to integrate a function, so here I'm really turning into an engineer. But if you were to integrate something that looked like this, naively, so k is some fixed integer, right? So this is a nice function, it's power series. Then you divide by, say, one of these things. What's going to happen when you integrate it? Say, around the unit circle.
It's supposed to be tens inside the,
Oh, thank you, yes. Yeah, that would be really stupid.
we only need to look at the negative.
And probably, I don't want them all to do the same term. There we go. What happens when you integrate this?
We only have to look at the negative first power.
That's right. Look at this. This is a power series, so to speak, and it starts with the negative k power, negative k plus 1. The only thing that matters is what's the coefficient of the x to the minus 1 term, right? Now that's very fast and loose, but that's essentially how things work. So Cauchy's integral theorems. If f of x is holomorphic just means you can write it as a power series. On some domain D open, and well, let me say everywhere on and inside some curve C. So it's nice, it's a power series inside here. Then the integral f of z over this curve is zero. So it's a power series, it doesn't have a negative 1 term. And number 2, in general, if f of z has a finite number of singularities, inside curve, then the integral around the curve is 2 pi I times the sum of what we'll call the residues. What are the residues? They are the z to the minus 1 term in the power series expanded about that 1. Right? Now, you can work this out, but I'm going to show you a quick way to find residues. for some simple functions, if you have, 1 over f of z, and f of z has a simple 0 at a, the residue at a is 1 over f prime of a. Just take the derivative and plug in where the problem is, not give you the reason. I'm gonna do this problem. This is magic. Okay, the first thing I need to do, I'm gonna tell you what my, I'm gonna tell you what my strategy is. I'm gonna integrate this in the complex plane, but of course, I just really want this real answer. So what I'm gonna do is I'm gonna put it on a big semicircle like this. I'm gonna integrate it this way. So the radius here is r. The bigger r is, the closer this part of the integral will be to being my answer. Agreed? Now my question is what is, if I call this contour gamma, what is the integral around gamma of dt over z to the 4 plus 1? Well, according to this, all we have to do is find out where this function, 1 over z plus 4 plus 1, goes bad inside here. Right? Complex variables help us again. This has got the problems of z to the 4 is -1. Right? And -1 is e to the I pi. And you can add any 2 pi multiple that you want. So z is e to the I pi over 4 plus pi over 2k. And so here's what I get. 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. And now I can stop writing because the next one's going to be 9 pi over 4, which repeats the first one. Everybody agree with that? This thing has 4 roots, and they appear roughly here, 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 and here. Agreed? By the way, Hussein came up with the magic factorization of the polynomial. You can use this now to put this back together and see where that came from. These two right here are complex conjugates. Look at x minus this, x minus that. Multiply them together, you'll get one of the polynomials. Look at x minus this, x minus that. They're complex conjugates. Put them together, you'll get the other. Right? So there's complex variable supplements a little bit. These two don't count because they're not contained inside the contour. Right? So I can forget about this. Right? Residues. They're given by 1 over 4 x cubed, well, z cubed, evaluated at e to the I pi over 4, e to the I 3 pi over 4. Right? Because those are the only ones that I care about that are in there. What happens when I figure out these residues and add them up? Sum of residues, let's see, it's going to be 1/4 e to the minus I pi 3 pi over 4 plus 1/4 e to the minus I 9 pi over 4. Agreed? Okay, let me see if I can get my pea-sized little brain into gear here. So I get 1/4 cosine 3 pi over 4 minus I sine 3 pi over 4 plus cosine 9 pi over 4 minus I sine 9 pi over 4. Agree? Now, notice the cosine 3 pi over 4 is right here, and now pi over 4 is here, so the cosines cancel out. Right, so these two suicide pact, they're gone. This one right here, 3 pi over 4. That is 3 pi over 4, isn't it? Right, this is minus 1 over radical 2, and minus outside 9 pi over 4 is going to be another, yeah, these are both. So I get 1/4. And this should be what? Minus I radical 2. Because that's a 1 over radical 2, and that's another 1 over radical. And 2 pi I times sum is 2 pi I times minus I over radical 2 over 4, which equals, let's see, that goes to +1, that cancels, and I get pi over, well, pi radical 2 over 2, which is pi over radical. And there's the answer. Right. No partial fractions, no me missing which polynomial that I'm supposed to put on the bottom, et cetera, et cetera. Now, there's one thing that might bother you. This is the value of the integral, but you don't seem to be going to infinity. Notice that this value, of course, around the contour does not depend on what r is. Agreed? So what happens if you let r go to infinity? Then this bottom integral, bottom piece becomes right? And the top piece, this goes to 0. How come? Well, remember, what are you doing? You're integrating this function. So everywhere this is measured 1 over t4 plus 1. So the value of this function is like 1 over r to 4 plus 1. And the value of the integral along this contour is bounded by this times the length of the contour. What is the length of the contour? It's about pi r. Everybody agree with that? So what happens? This integral is bounded by the length of the contour times the maximum value of the function. So it's bounded by pi r over r to the 4 plus 1. That thing is less than or equal to that. And what happens to pi to the 4 over r to the 4 plus 1 as r goes to infinity? It goes to 0. It basically behaves like 1 over a cube. And that justifies it. So there you go. So any of you undergraduates or even graduate students, I would highly recommend taking complex analysis. It was in my undergraduate school, it's required of all the engineers, and it's a very, very powerful tool and lots of fun too. When I first learned how to do this stuff, I'll show you what an exciting social guy I am. I got one of those like integral table things that has all the indefinite. I used to say, you know, what are they smoking? I mean, where did they come up with this stuff? When I found I could use this stuff, oh my goodness. I went through and I think I worked out all of the integrals. It was more fun than you can imagine. Okay, any questions? All right, well, y'all have a good weekend. Stay warm and dry, and we'll see you next week. Any questions out there? All right, see y'all.